right, exploring light and color. Today we are going to be talking a lot about the electromagnetic spectrum. How many people use the electromagnetic spectrum in their teaching? Really? Okay, I think you probably use it more than you think. All right, we'll do various things. All right, so here's a question for you. All right, and I want you to come up with some crazy type of answer or whatever. What is the relationship between light and exploration? Anybody have something that they would throw out? Yeah, this is not all lecture, okay? There is some interactivity here, okay? You actually have to get your brain started. I got my brain started now, so yes?
Well, changes in the frequency of light tell us how things in space are moving.
Okay, so we can use light to see how things are moving in space, okay? What other ways might light be associated with exploration? Yeah?
The distance, maybe from each other.
Okay, distance. All right, we can try and look at, I guess we can, if we could measure the time the light takes from something, we could measure the distance, right? Okay, because we know the speed of light. All right? Yes, up down front.
Composition.
Composition. We can measure composition. How?
By looking at which wavelength or frequency is there or has been absorbed.
Okay. We're talking emission and absorption lines. Okay, right, good. All right, there's a more fundamental nature to light and exploration connection, all right, that I want you to truly recognize. All right, when Magellan, or well, let's go with Columbus, okay, we just had Independence Day. Let's go with the old explorers. When they wanted to know what's out there, what did they do? Columbus and Magellan, what did they do? Huh? What did they do? They got on a boat, and they went there, right? Well, I'm an astronomer, and I want to know what's happening in the Andromeda Galaxy. So can I get on a boat and just go there? It's a proverbial slow boat to the galaxy, right? I cannot get on my boat and rove my way all the way to the Andromeda Galaxy to check out what's happening there, okay? How am I supposed to understand what's happening in the Andromeda Galaxy?
You look
I look at what?
through a telescope.
Through a telescope, and what comes through that telescope is
Light.
light. Thank you. Okay? It's Monday morning, so I do have to start pulling you through this. But that's the real fundamental thing that you have to recognize, that all astronomers have for almost all of the universe. There's a few places we can go visit. Okay? What's the most distant place in the universe humans have visited? The moon. Okay? That's basically our backyard. All right? Then we have sent robots. How far?
Mars.
We've gone to Mars, yes.
Yeah.
We've gone to the asteroids. We've gone a little bit further than that.
Consider satellites robots or not?
Well, space missions, robots.
Voyagers.
Voyagers. All right, the Voyager missions, I consider them robots. They're space missions, okay? And they've gone where?
Pluto.
We're going past Pluto next week, okay? All right. We've actually gone a little further with the Voyager missions, although New Horizons will overtake the Voyager missions because it's moving faster, okay? But we've gotten out to about 125 astronomical units, which is 125 times the distance from Earth to the Sun. Okay, something if you want to write down, astronomical unit, AU, is the distance from Earth to the Sun. We'll use that a bunch of times this week, okay? All right, we've gotten out to 125 AU, which is kind of cool. All right, that's the most distant we've gotten into the universe. Anything beyond there, we have to explore only by the light that it emits. Okay? We have to explore it by the light. So astronomers, it's fundamental for us to be able to pull information out of light. Okay? We take light, we bend it, we stretch it, we transform it. We do everything we can to try and pull information out of light. That is our exploration. Okay? Our exploration totally is light. Oh, wow, we're going to have sun shining through. Actually, that'll go away in about an hour. Oh, well, not much we can do about that. So we have some light interfering with our light exploration. Okay, so here is a picture of the night sky. All right, and there are those stars. And if we want to understand what's happening at those stars, we have to transform their light in many ways to figure out what's going on with it, okay? So, we have another star that's nearby. It is the sun. Very good, okay? And what you can see in this is that, what color is the sun? All right, so how many people, I heard some yellows. I heard some orange yellow. Any other? What does it look like in this picture? It's white. Why is that? Huh? Filtered? No. Okay, here is where I tell you that you've been lied to all your life. Okay? You are told the sun is a yellow star. This is how you will see it. It will appear on NASA websites with this coloring on it. And this is a lie. This is not what the sun looks like. Whenever you ask a kid to draw a picture, he's got a house, and he's got the grass, and he's got this blue sky, and he draws in a yellow sun. Okay? And he doesn't realize he's falling into a trap, a misconception. The sun is not yellow. The true color of the sun is that. If you take the black body function for a 6,000 degree object, you pass it through the RGB filters that represent the human eye, this is the color you get. Well, of course, you then have to pass it through that projector in my computer, so it's probably slightly off from this, but this is a decent approximation of it. What color does that look like? White. Yeah, it's slightly peachy white is what it really is. All right, so you have to go to a paint store to actually find a good paint chip to match it. I've been thinking one of these days I might want to do that. But that's what the true color of the sun is. All right, why do we think it's yellow? Okay, all right. Well, we'll get to that in a second. Let's see, where's my slides? Okay, all right. So that white is partially white because it's an overexposure, okay, since it's blown out the detector. All right, since it's so bright compared to everything else around here, it blows out the detector, it's going to go white. But it's also white because, well, it actually really is white. So we try to address a few misconceptions. One of them is, well, then we've got this blue sky around here. If the sun is white, okay, and it's illuminating the sky, why is the sky not white? Why is the sky blue? Okay, have you ever, all right, let me ask it easier, okay? Have you heard a misconception about why the sky is blue?
I heard it reflects the ocean.
Because it reflects the ocean, okay? How many people have heard this one? Fewer and fewer over the years, okay? I've heard it when I was a kid, all right? And this is a great one to ask, okay, well, if the sky is blue because it reflects the ocean, then why is the sky blue in Kansas, where there's no ocean anywhere nearby? Okay? Not that, let's not Kansas bash right now. There's always a temptation to do that. All right, anyways, so the sky is blue simply for the same reason that sunsets are orange and yellow, okay, and red. Because the light from the sky comes not from reflecting all of the sun's light, but by its scattering differentially, all right? It scatters the blue light more than it scatters the red light. So if we go back to the blue sky picture, okay, the sun is over here somewhere, and the light is coming and hitting the air particles. The blue particles are the correct wavelength to scatter the sun's light. So the blue light scatters more off of the particles in the air. The red light passes through more. So when you look at sunset, you see red because the blue light is scattered out of what you're looking at, okay? So the sunsets are red not because there's extra red added to the sun's light, it's because there's blue subtracted from the sun's light, okay? So that's why sunsets are red and the sky is blue, which allows me to also show you why you think the sun is yellow. because when you view it at sunset, which is the only time that a lot of time people view it, it starts to look yellow because you've scattered the blue light out. Okay? So this is my opinion where that yellow sun came from. We also, in astronomy, are responsible for it. Mea culpa, we have called the sun a yellow star. Okay? Just because we classify it as a yellow star doesn't mean it actually looks yellow. I'm sorry, that's one of the vagaries of astronomy. We have red stars and orange stars and yellow stars and blue stars and white stars, etc. And they don't actually have those exact colors. It's a shorthand for astronomers to recognize where's the peak of the black-body curve. And for the sun, it's not in the yellow, it's actually in the green, but it's close enough to yellow. Nobody calls green stars, all right? So for the sun, it's actually white. We call it a yellow star. At the sunset, it looks yellow, but if you really measure it, it's really white, okay? Especially if you get up above Earth's atmosphere where you've got no transformation to it, you can measure it and see that it's purely white. All right, so where are we headed with this? Because the sun is not actually just white. White is actually all the components of the rainbow, right? Okay? So when we think about color, it's not always so straightforward, okay? Even our everyday phenomena has more complexity to it. How many people have seen a rainbow? Okay, good. All right, ask your students that, because it's surprisingly how many people, when I ask that question, have gone, well, I've seen it in movies and pictures, but they actually haven't seen it. It's a fundamental thing, and I love it. I think that the best rainbows you can consistently see at the waterfalls, because the mist comes up and always catches it, and you get these beautiful rainbows, especially in Yosemite. There's a great the falls in Yosemite, and you get the rainbow, and it's great just to go to Yosemite anyway. So let's take a class trip to Yosemite, and we'll go see a rainbow. Nah, unfortunately, that would take all week. All right, so we can see that white light breaks up into all the colors of the rainbow. All right, and we know this, the way the kids still recognize this is from Pink Floyd's Dark Side of the Moon album cover. I did this with some 8th graders expecting to have to say, well, your mom and dad and I, we used to listen to this music, and they actually still know this, okay? I don't know why they still know this. This is familiar. This is not exactly correct, of course, in terms of a prism, okay? It's much too clean. You can call this a graphic of how a prism operates. It's not exact. Here is a real prism, okay? Picture of white light coming in and pulling out into the various colors. You will notice that how it's nice and even and smooth in the diffraction here. Okay, it's not quite, it's not quite so even and smooth. And you can see how it spreads out the wavelengths differently, right? Okay, different wavelengths of light refract differently inside the prism, okay, creating the rainbow. And if you want the full view of it, here's a prism, and you can see the white light coming in and the refraction here to produce the prism. There's also reflection. At every interface, there's refraction and reflection. Okay, refraction, bending, reflection, bouncing. Okay, so you can see an internal reflection coming out. You can see a secondary rainbow over here due to some other internal reflections and then refractions, etc. So, of course, those of you who teach physics can get things as complex and detailed as you would like. All right? So, conclusion. White light is composed of all the colors of the rainbow. That took a long way to get there, didn't it? I mean, you guys knew this going in, but it's nice to see all the details of it. All right? Well, let's prove it to ourselves. We're going to do some demo. All right. First of all, Joey, can you kill all the... Well, I don't know if that's going to help. All right, let's do this. All right, let's leave the lights on for right now. Okay, so we have a light strip of LEDs here. All right, and in the red there, what color do you see?
White.
White. Okay. All right. How about this one? What color do we see? Red. And then, what about that? Okay, that's supposed to be orange. Let me just tell you that. I got to prep you for these things because the light strip doesn't produce pure colors nicely, okay? This one, there we go. That's orange. and that's yellow, okay? And let's see here, we got this one, green, and then we have, all right, this is blue, and this is teal, turquoise. All right, the color that we usually call this is cyan, C-Y-A-N, cyan, and finally, magenta, violet, purple. It's supposed to be violet, okay? All right, so we have a LED light strip that produces all the various colors of the rainbow. Okay? Now, here's what we're going to do. We're going to take these clear glasses that you have. We're going to put them on, and then you're going to tell me what colors you see. All right? Let me move around the room so we can do this. Okay, you guys have been quiet over here. Somebody, tell me what you see. Red, blue, and green. Okay, anybody see any other colors? Huh? You still see some white, okay. All right. Anything else? Orange, I hear. A little bit of violet. A little bit of yellow. Okay, this is what we let's try that. That help? All right, that definitely does help. All right, let me also, do not look over here. Don't look here. All right, we're trying, this is where having, does that help as well? So everybody can see it? All right, everybody got this? See multiple colors. There are some strong colors and some weak colors. All right, what you're going to see, it looks something like this. Okay, where you've got the LED strip down the center, you're still going to see that white, but you're going to see a rainbow on either side of it. Everybody okay with that? Say yes, humor me. Thank you. I need lots of encouragement, okay? All right, so when we look at white light, we break it up into its component colors. What are these glasses? Do you know what these glasses are? Okay, physics, who's a physics teacher here? Huh? They are diffraction grating glasses, okay? The white, the clear plastic has been scored with very, 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 very fine lines, okay? And using that, it acts as a diffraction grating that spreads the component colors of the light out, okay? It does, on either side of this, create a rainbow due to diffraction, not refraction, but it's close, it gives you the way of seeing a prism. All right, so we're going to do some spectral observations, okay? We're going to look at the various colors of light. White, all right, with white, what did we see? All right, now, we noticed that red, green, and blue were strong, and then we said, well, sort of some yellow, sort of some orange, and sort of some violet. That's my notation for that. Let me give you one major caveat to everything. I am not always correct. You are allowed to disagree with me. Science is a lot about disagreement. Okay? If everybody agreed, we wouldn't have any research to do. Okay? I will have my answers that I did one day long ago, and if you disagree with them, please speak up. I want to hear disagreement. Okay? Trying to get the correct answer is foolish in my point. I want to know what you see. I also want to know if your eyes are different than my eyes. Okay, is anybody here colorblind? Okay, we have 25 people. About one of you should be colorblind, actually, statistically, from what I understand. Great. Well, we don't.
I'll be
All right,
colorblind today, Frank.
What? John will be colorblind. Okay. All right. Or you can be like Stephen Colbert. He doesn't see color either, right? All right. In a different sense. Right. Okay. So where do we start? I started with violet. Okay. So everybody, glasses down. All right. So this is our violet. Okay. We see that's violet. Now glasses up. Tell me what you see. All right. Let's ask people in the back of the room. In the blue here.
Blue and red and maybe a little orange.
Blue, red, and maybe a little orange. Anybody see any other colors?
I see green.
Oh, a little bit of green.
Violet.
A little bit of cyan. All right, a little bit of violet. Okay, so we agree that the dominant ones are blue and red. All right, and a little bit of other things. Does anybody see yellow? I didn't see any yellow. All right, so we all are okay with not seeing any yellow. All right, I saw a little bit of orange. Now, one of the other things that you must be aware of when doing this exercise is that the lighting conditions will affect what you see. If you have extraneous lights on, it changes the way you see it. If you have the sun shining in through a window, it will change the way you see it. How dark your room is will change the way you see this, okay? All right, glasses down, and let's go to blue. That is what's supposed to be blue. All right, glasses up. Show me what you see. Tell me what you see. Hold on. I'm going to ask one person to start. Over here in the red. He sees blue. That's your dominant color?
Yep.
Okay, great. He sees blue as the dominant color. What other colors do we see? Everybody? Green, cyan, violet.
Yeah, red and yellow.
Red and yellow faint.
Coming off the window.
All right. That might be coming up. Yeah, once I do apologize. You guys right here, I wish we're going to hire some big guy named Vinny to stand there and block that light. If you want to move over to this side, you can. All right? Okay, so what did I see? I saw, I saw blue, and then I saw a little bit of everything else. Okay, tiny amount of everything else. We'll see how that, all right? Again, you're allowed to disagree with me. Okay? All right, glasses down, and we will switch to cyan. See that as cyan? Now glasses up, and let's see, who have we talked to? How about you in the blue here? We talked to,
Sure. Well, I see
what's your dominant colors, first of all?
blue, yellow, a little bit of red, and a little bit of green in there too, between the blue and yellow.
Blue, yellow, a little bit of green, a little bit of red. Okay, other people? She says blue and green. You say? She says violet.
Oh, I can see the violet now on the inside.
Okay, a little violet over there. Anybody, any other colors? Okay, so what do we see? I saw blue and green as the dominant ones with a little bit of everything else as well. Okay? Again, my viewing conditions are different than your viewing conditions. I actually had a very darkened room when I did this. I was probably sitting in my office with all the lights off and only doing this. Okay? All right, glasses down. We will change it. Everybody see green. Okay, glasses back up. We need somebody over here in the yellow shirt here. That's you.
Orange, I'm going to disagree with you.
You're going to say that's orange. All right, mustard colored shirt. How about that? Can you see that well from over here?
Yeah, lots of yellow and green.
Yellow and green,
Faint orange and blue.
faint
Bluish.
orange and blue. Okay? She sees faint red. Anybody else? Any other colors? Oh, what did you say back here? Just green and red. Okay. All right. What did I see? I saw green as the dominant color with a little bit of blue, yellow, orange, and red. And I saw no violet. Does anybody see any violet? Okay. Okay, glasses down. Let's take a look, and we'll go to yellow. Okay, glasses up. Let's see, where do I need to be? How about over here in the striped shirt? Did I ask you already yet?
Red,
Okay.
Red and green.
He says red and green are his dominant colors per yellow. All right, what other colors do we see?
A little bit of blue.
She says a little bit of blue. Little yellow. Maybe, all right, hold on. Glasses down for a second. She just said, it's yellow, right? And she's saying, maybe I see a little bit of yellow. Excuse me, what? Maybe I see a little bit of yellow when it's yellow, put the glasses back up. How much yellow? No, I'm serious. How much yellow do you see?
Not very little bit.
Isn't that funky? All right. Wouldn't you expect yellow to be a lot more? We're seeing dominant red and green, and I put no yellow actually. Okay? This is funky. All All right, when I did this, I didn't see any yellow. I only put a little bit of orange and a little bit of blue. That's kind of funky, right? This is your color combination producing things. All right, glasses. All right, glasses down. We're going to go to orange. All right, glasses up. How about the guys in the back of the room, the slackers sitting back here? What do you guys see? Tell me what you see for orange.
Green, red, and a little yellow.
Green, red, and a little bit of yellow. Okay? Anybody see anything else? Did I hear blue?
Yeah,
A little bit of blue. Anything else? Okay. All right, so what did I see? I saw green and red with a little bit of yellow, a little bit of blue and orange. Now wait a minute. Isn't that the same thing we had for yellow? How come yellow and orange have the same colors? Let's take a look at it. Glasses up. That is orange. This is yellow. That is orange. This is yellow. Orange, yellow. Orange, yellow. Orange. What is the difference between yellow and orange? Back of the room there. What's the difference?
The intensity of green.
The intensity of green. How many of you would have expected before we started this exercise that yellow and orange, the difference between yellow and orange is green? Kind of fun, all right? The fact that you don't see any yellow when the color is yellow, and the fact that the difference between yellow and orange is green is kind of cool.
Can you flip those back and forth a couple more times?
Want me to go back and forth? Oh, you're putting the glasses in front of the camera. Okay, so there's yellow, and there's orange. And there's yellow, and there's orange. Okay, glasses down. We will get to our final color, which is red. There we go. Glasses up. Okay, I haven't talked to you guys in the front row here. What do you see? She sees just red. Anybody see any other colors? A little bit of orange, I guess. Any others? Okay, so we got red and a little bit of orange. Let me see what I saw. That's what I saw, red and a little bit of orange. Okay, glasses down. Let's take a look at our chart here. All right, our astronomy teacher over here. What do you notice about this chart?
We saw a little bit of orange in every color.
A little bit of orange in every color. All right. There's a little bit of orange in everything. That sounds good. Okay, I like that answer. Let's see, in the black here. What else do you notice about this chart?
The blue, green, and red.
The blue, the green, and the red are dominant. Okay? The only place we have big X's here are blue, green, and red. Okay? All right. Anything else to notice about this chart? Anybody?
Red's involved in all.
Red is involved in all as well. Okay, good, good. And blue and green are involved in how many of them? All but red. Okay? All right, so if I show you this white strip now, tell me, what do you think is going on inside this white strip? You on the end there.
You have all of the colors sent out.
Okay, all the colors are being sent out, but what's physically behind the sending out of those colors? All right, this is an LED light strip. What color LEDs do you think I have there?
Oh, blue, green, and red.
Red, green, and blue, green, and red. You are correct. Okay, when you look at your cell phone and you see a color image on your cell phone, are you really seeing lots and lots of different colors? Or are you just seeing red, green, and blue? You're only seeing red, green, and blue. The color screen of your phone is composed of red, green, and blue dots. This LED is composed of red, green, and blue LEDs. Your television is composed of red, green, and blue. When you digitally produce color, you decompose it into red, green, and blue. Anybody who works with image processing, Okay, you get a JPEG image. It's got values for red, green, and blue inside that JPEG image file, which your computer screen turns into lots and lots of different colors. Very important thing. One is that white light is composed of all the colors of the rainbow, but digital light that we create these days is actually composed of varieties and intensities of red, green, and blue in order to create those colors, okay? Our color space has a red axis, has a green axis, has a blue axis, and where you exist within that three-dimensional color space can give you a wide variety of colors. Not every single color can be done like this, but a very wide variety of colors, okay? Yes, we had a question.
Yeah, I think a while back, Sharp TVs were being made with a yellow LED too.
There are the Sharp Aquos, AQUOS, has a 4-gun system. The NHK in Japan has developed a 6-gun system. And there have been people playing in research with up to a 10-gun system in terms of using, trying to get your color spectrum across there. All right, somebody in the back has something to add to it.
So, any idea why they went with yellow instead of orange? Since orange is in everything and yellow's only in.
I do not know. What is that?
What's that?
Huh, that's my PowerPoint wigging out. Maybe I need to reboot my computer because that happened last time my computer got tired. My computer gets tired and PowerPoint wigs out. Yeah, I don't know why they went with yellow instead of orange, but I do know that the Sharp system had red, green, blue, and yellow to add a broader range of colors. And what they would show is here's what it happens with a four color system and versus a 3-color system, and you could really see the colors were more vibrant, and you could get a wider variety. Yes.
We looked at our cell phones under microscopes.
Oh, great.
Last year, and you can actually see the little tiny pixels. And the older the phone was, the bigger the pixels were. And then somebody had the new, I don't know which new phone it was, and you could tell the difference between like an iPhone 4 and an iPhone 5 and an iPhone 6 as far as the pixels getting smaller. And then there was one person that had a phone that actually had 4. They had a yellow pixel.
Oh, really?
in there.
Cool. Well, that's an expensive phone, probably.
Yeah.
Yeah. Okay. Cool. Yes.
My teacher told me to save money, don't buy anything other than blue, yellow, and red tubes of color. It was really fun.
All right. Let me say this louder, okay? Her art teacher said, don't buy anything besides blue, yellow, and red because you can mix those and get every other color. All right. We remember when we had crayons, right? And you draw in the blue and you draw the red on top of it, and what do you get? Yellow with red, you get that. Blue and red makes purple, right? And you can see how by additive color, you can create lots of different colors, right? That's how all of our things are going. But it has a very important implication for astronomy, all right? When you take a picture with your iPad, okay, are you taking a color picture? You think you're taking a color picture, but you're not. You're actually taking a red picture, a green picture, and a blue picture all at the same time. All right? You're taking 3 different pictures, and your iPad or whatever your camera is combining them together into one picture automatically for you. All right? We are always taking red, green, and blue differentials. Now, here's something that you're going to learn about in just a bit. Hubble only takes black and white images. Okay? The Hubble Space Telescope, as expensive as it is, only takes black and white images. But if we want a color picture from Hubble, we need to take a red picture, and then a green picture, and then a blue picture, and add them together. Or we take multiple pictures together and add them together to make a color image from Hubble. All right? But you are still doing the same thing when you take a picture with your cell phone. All right? Cool. Let's move on.
You want to switch out laptops?
Hold on. PowerPoint just crashed. I expected it was going to crash on me. PowerPoint has encountered a problem and needs to close. Okay, so let us get back to this, where PowerPoint crashed. All right, our conclusion for this section. The color of light you see may actually be a combination of the various colors of the rainbow. Okay? Just because you see orange, all right, doesn't mean you're that actually orange is what's being emitted. All right, great. So, I've gone through a bit of this already. Hubble takes its images. One important point to recognize for Hubble is only 350 miles above your head. How far is that? Well, if this is the Earth. Earth is what, 6,478 miles in radius. So Hubble's orbit is like about that. Okay. So, all right. One thing to get in your head is that Hubble is in what's called low Earth orbit, not very far above Earth. A lot of kids think that Hubble flies out, takes a picture of a target and flies back, and flies out, takes a picture of a target, or that it's way, way, way out in deep space. Okay, this is what we call low Earth orbit. It is the height to which the space shuttle could reach. All right,
Then
there.
why does it,
Oh, sorry, go ahead. No, please.
then why does it take so long to give instructions?
Huh?
Why
It doesn't. It doesn't take so long to give it instructions. The communication with it is nearly instantaneous. Okay, 350 miles is the difference from here to Boston. Okay, so the time it takes for us to get a signal from here to Boston is about the same as it does to go from here to Hubble, right? But the point is that we have to schedule the time so carefully that we, in order to figure out that problem of scheduling the time carefully, we do it 11 days in advance. That's why that's why it's 11 days in advance, because the scheduling problem is so difficult. Okay. All right. So here's a picture of it. You can see Hubble here, and you can see that atmosphere. All right. That atmosphere. You see that sort of haze? Every ground-based observatory has to look through that haze in order to look at the universe. Does Hubble have to look through that haze? No. Okay. Hubble's main reason why it is such an amazingly valuable telescope is because it doesn't have to look through that haze. It has a clearer view because it's located above Earth's atmosphere. Okay. All right. Here are some basic information about it. Actually, the orbit period is down to about 96 minutes. As it decreases, it gets slightly shorter. All right. Hubble looks at planets. This is an image of Mars. Nothing spectacular. We've gotten better ones from in orbit around it, but it's the best we can do from Earth. We've looked at Saturn. We've followed it over the course of the years. You can see Saturn's rings tilt from our perspective as the years go by. We look at star clusters. This is the globular star cluster Omega Centauri, over 2 million stars in there. Amazingly detailed. Hubble can see the detail inside there. We look at newborn star clusters. This is a cluster of bright blue stars that have just been born from the gas cloud, and the gas is eating away the gas cloud from which it formed. Here is one of those pillars on the edge of that gas cloud. You can see the detail of that. Hubble looks at nebulae. This is a planetary nebulae, which is actually nothing to do with planets. It's actually a dying star. Here is the dead cinder of the star in here, and this is the outer layers of the star blown off like a smoke bubble into space. Here is one that has exploded in a supernova explosion, and you can't see the dead star in there, but out here are the guts of the star that have blown across interstellar space. Yes?
On the previous photo,
Yes?
the star in the very center, like, I mean, that's what it looks like too. It's like the center of that's where the Death Star is.
Yes,
that's not one that from behind.
Huh? It could be. Great question. Okay. So why couldn't it be the dead star, and why is that one? Well, it's in the center, and this actually blows out relatively symmetrically. Okay. So that was why we know that. We also do a spectral. We look at the characteristics of that star. It has the characteristics of what we call a white dwarf, and so this one presumably is a background or foreground star that doesn't have characteristics of a white dwarf. Okay? Yeah. Great. So supernova explosion, this is a supernova remnant, the gas from that. We look at galaxies such as a barred spiral galaxy. Okay? We also look at active galaxies. You can see this red stuff. This is a specially processed image where you see the main disk of the galaxy, and then the hydrogen alpha shows you actually some star formation that's blowing out material from the core of the galaxy. There's so much star formation that material is actually getting pushed out of the galaxy. We look at galaxies that collide. We'll talk about that a lot on Thursday. We see groups and clusters of galaxies and galaxies. This is a giant cluster of galaxies with thousands upon thousands of galaxies. And a really cool effect called gravitational lensing, which we'll discuss on Thursday. And then on out to the edge of the universe, this being the Hubble Ultra Deep Field, looking as deep as we've ever looked in visible light into the universe. Okay, so Hubble does all sorts of things from planets to stars to nebulae to galaxies out to the edge of the universe. And as I said, it creates all these gorgeous, pretty color pictures, but every single one of these color pictures was a black and white, as a combination of black and white images. Okay, so let's do we take a look at that. Oh, so this is where I want to make that point. Okay, so here's the Mars image, but its original data is as black and white images, which Zoltan LeVay, who is sitting in the back of the room now, will tell you about in just a few minutes. So, astronomers use filters to observe only selected wavelengths of light. How we create those color images is that we take the light from the object, we filter it to get the red, the green, the blue, or a variety of other filters that we'll talk about a little bit later, in order to get the colors that we want. If we're going to create a color image, it's going to be a combination of these various filtered images. Okay? So, demo number 2. Okay? This will go a little faster because we're just going to do some. All right. So first of all, we got the white light up. Now, let's put up our blue glasses. Everyone got their blue glasses on? All right. Blue glasses. What color do we see with blue glasses, sir, here?
Blue.
He sees blue. Everybody agree? We see blue. All right. Let's put up our chart. So with the blue glasses, do we see blue? Yes, we see some bright blue. Okay. Do we see any other colors? No. Okay, great. All right, let us go to violet light. Okay. And this, anybody can just shout it out when I ask these questions, okay? Because we're going to go through this pretty quickly. Violet light, what color do we see?
Blue.
Is it bright?
Yes.
All right, we see bright blue. What did I say? I said bright blue. All right, let's make a prediction. We're going to go to blue. What are we going to predict we're going to see? All right, let's try it. Blue. And what do we see? Everybody together. There we go. Bright blue. Okay, now we will go to cyan. All right, there's cyan for you. What colors do we see with cyan? Blue. Is it bright or faint? Bright blue for cyan. In my test, I agreed with you. Now let's move on to something. Let's try some green. Okay, what do we see for green? Green. You see green? Okay. All right. Anything else? Bright? Faint? Okay. All right. I saw green as faint. So let's see. If I go back to cyan, all right, that's bright blue, and I go to faint green. Does that make that you agree with me? You're allowed to disagree with me. Please disagree with me.
It's dimmer, but I wouldn't consider it faint compared to your previous observations.
Okay. You would consider it faint compared to the previous, but you wouldn't...
Not compared to the one where you use diffraction grading.
Not compared to the diffraction grading. Okay, great. All right, but in this gradation, we'll leave it alone for that. All right. Let's try yellow. What do we see?
Green.
Green. Bright or faint? Faint green. Okay. I agreed with you. You guys are good. All right. Let's go orange. What color? Green. Bright or faint? Faint. Okay. I said green faint as well. I'm doing well. I'm agreeing with you. Actually, I think I should put it this way. Okay. Finally, we will go to red. What color do we see? Faint red. All right. In terms of faintness, is it the same faintness as the green was? He says it's more faint. Okay? Because I think I said very faint. Okay? I had 3 brightness levels. I gave them very faint, faint, and bright. All right, glasses down. Let's take a look. All right. The only thing we saw as bright was blue. Okay, but we saw a little bit of, and then we saw a tiny bit of. Okay, so what is happening here? You in the white sweater. All right, what do you think is happening here with the glasses?
The blue is bringing out the blueness.
Okay. It is it's allowing through the blue light, right?
Yeah.
All right. Is it a perfect blue filter?
No.
What do we think? In the pink here, what do you think is going on? Is it an expensive astronomical grade filter that we paid thousands of dollars for? It is not. Okay, it is something we got as cheaply as possible because we know that school supplies are not something you have tremendous budgets for. Okay, so do you think if we were astronomical grade, we could design a filter that only did blue? Yes, we could. All right, and then you wouldn't see any green or any red, but this is not a perfect filter. It does let through some other colors. All right, so the idea is that all right, and this is really important, okay? Because here's a misconception. Some people think that when you put a set of glasses like this in front of you, it adds color to it. Okay? It didn't add any color to the red. You can't see blue when looking at red light, can you? So it doesn't add blue to the light. Rather, it subtracts away everything but the blue. Got that? Really important clarification to make, because when you talk about looking through rose-colored glasses, oh, everything looks red. Well, only if it actually emits some red. If it doesn't emit any red, then it won't look red. Okay? You can't make something look red that isn't red, that isn't emitting red already using filter glasses. We got that? Okay, important thing to get in your students' heads. All right, let's take those rose-colored glasses and let us take a look through the red glasses, okay? Let's go very quickly through this, all right? So, when we look at white light, what do we see? Bright red. Bright red, very good. When we look at violet light, what do we see? Bright red. When we look at blue light, what do we see? Faint what? Faint violet, okay? They say faint violet, I said blue very faint, okay? Who disagrees with me? Yes. She says violet. I don't know. Let me take a look myself.
Maybe it's because you look at it in a darker light.
Yeah, I have to agree. In this environment, it looks more violet than blue.
But if you look
Okay.
at them as you go down the line, the LEDs aren't all lined the same. So like the eighth one down is actually still red for me, and then you get some whites and some blues, and then top and bottom's bright.
All right, now, yes. I agree that not all of the LEDs are perfect. Matter of fact, one of the reasons we're hanging it like this is because there are some LEDs on the back side that are actually totally broken. We found out last time we did it, and like, oh yeah, those first 6 ones, they're distorted. So I apologize for the imperfectness of our equipment. But you're teachers, you know you have to deal with that. All right, cyan. Here's cyan. What do we see? Faint what? She says it's almost white. What do you say? Light violet? Okay. All right, what did I say? I said blue, very faint. We'll change that to violet, very faint for today, okay? All right, what's next? We got to go green. How do we see green? Orange, faint orange, okay? What did I say? I said orange, very faint, okay? And we got green, let's go to yellow. Bright red, okay? Orange. Bright red, I agreed with that one. I'm better. Sorry about my blues, that should have been violets. All right, and finally, anybody want to predict what we see when we go red? There's red, and we do see bright red. Yes? Yes, okay, so very good. With the blue filters on, what is the only thing we see bright is? With the red filters on, the only thing we see bright is? Red. Very good. We can see what filters truly do. All right, so our conclusion, a filter only allows only certain colors of light to pass through. All right, so that is your basic color science. They call it color science. There's a lot more. The gentleman in the back of the room, who is our next speaker, will tell you all sorts of cool things about that. And I'm sure he could go on for much longer, telling you even more. But let us take, what time is it? I can't see. Let us take a 5-minute break for going to the bathroom. We will start again at 9:45. Thank you all.